Hello dear students, welcome to Pen and Paper Chemistry on YouTube. We are now concentrating on today's lesson, that is lesson number 3, where we are dealing with the heading oxidation states. When we talk about the oxidation states of the D and F block elements, and specifically we are talking about the D block elements over here, we notice that there are variable oxidation states being exhibited by the elements of the D block. A tabular form of the various oxidation states shown by the D block elements is there in front of you. If you notice, there are some very interesting features. First of all, unlike the P block elements, wherein we had the example like lead showing valencies of 2 and 4, plus 2 plus 4. Tin showing valency of plus 2 plus 4. If you notice here, the variable valencies are differing by 2. Whereas in the case of D block elements, you notice that the valencies or the oxidation states are differing by 1, 2, 3, 4, 5, 6, right? So first difference. Second, oxidation state plus 1 shown only by copper. Very easy to explain because it has S1D10 configuration, so it is able to lose only one electron so that the stability of D10 configuration is not disturbed. Plus 2 shown by maximum D block elements, right? So plus 2 plus 2 plus 2, and D block because we are just taking the 3D series, and similar behavior is seen in the case of 4D and 5D elements. So plus 2 is quite common, very clearly explained by the S2 configuration in the elements, right? Coming to plus 3. Now, if you notice, scandium shows only one oxidation state, and that is plus 3. How do we account for this? 4s2 3d1. The energy difference between the S and the D orbitals in the case of scandium is so low that it tends to lose all 3 electrons in one go, giving it an oxidation state of plus 3. All the other elements are showing plus 3. Copper shows plus 2, doesn't show plus 3. Now somebody must be wondering that if you've got D 1, 2, 3, 4, and if in order to show an oxidation state of plus 2, what does it do? 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10, right? In order to show an oxidation state of plus 1, it gets rid of the S electron. In order to show the oxidation state of plus 2, it gets rid of another electron from the D orbital. Now, if it is doing away with one electron, why not other electrons from the D orbital as well? Please remember here that with every electron moving out of the atom, the nuclear charge is increasing. Now, because of that increase in nuclear charge, the force of attraction for the other electrons will show an increase, making it all the more difficult for that particular atom to lose electrons further. Come to zinc. Only oxidation state plus 2, no other oxidation state. Can you explain? Very good. The S2D10 configuration, in which it tends to lose the S2 electrons but is not ready to disturb the D10 configuration. Although even copper had a similar case where it had D10 configuration, but copper is still okay with it, but not zinc. Go ahead in the 3D series or in general the D block elements, we notice that the number of oxidation states being shown is increasing. See, it's on the rise. Here it's only showing 1 oxidation state. Titanium is showing 3. Vanadium is showing 4 oxidation states. Chromium 5. Manganese, middle of the series, shows maximum number of oxidation states starting from 2 to 7. Very clearly explained by the fact that it has most number of unpaired electrons. So if you write the configuration of manganese, you will notice that it has 1, 2, 3, 4, 1, 2, 3, 4, 5, 6 and 7, right? So because it has 5 unpaired electrons in the 3d orbital and it has 2 electrons, a pair of electrons in 4s, which it is happy to give away, it has the maximum oxidation state of +7. Again, as we advance towards the right, the number of oxidation states being shown by the elements again shows a fall. Why? Because the electrons in the d orbital start pairing up. Simple. It would do you good to draw this table yourself and try to give reasons for this behavior on your own rather than looking for answers, right? Now, concerning the oxidation state, I would like to take up something interesting over here. If you see your P block elements, carbon, silicon, germanium, tin, lead, here what happens is you notice that the higher oxidation state, so as in the case of lead, the higher oxidation of +4 is not so common, it's not so stable. Due to the inert pair effect, they have a tendency to show more of the lower oxidation state as you go down in any group of the P block. On the contrary, in the case of transition elements, especially from group number 4 to 10, what we notice is as we go down, the stability of the higher oxidation state actually increases, right? So you will have the higher oxidation state being shown by the heavier elements compared to the ones which are at the top in any particular group. What explains that? Let us try and understand it. This can be explained on the basis of their ionization energy. We have taken a very simple example over here. Take the case of nickel and platinum. The total sum of ionization energy 1 and 2, that means the sum of the first and the second ionization energy for nickel and platinum is tabulated over here. Nickel is 2490 kilojoule per mole, platinum is 2660 kilojoule per mole. In other words, very clear from here, the numbers here. For nickel, the amount of energy required to remove the first 2 electrons is lower as compared to platinum. With the result, what we will find is that nickel in oxidation state 2 is more stable than platinum in oxidation state 2. Let's compare the sum of the first 4 ionization energies. That means the amount of energy required to remove 4 electrons from the atom. Now in the case of nickel it is 11290, whereas in the case of platinum it is 9360. Now what is lower over here? Platinum. That is why we notice that in the case of platinum, it is easier to remove 4 electrons compared to nickel if we have to remove 4 of its electrons. So this shows that platinum, which is at the bottom of a group, in its +4 state is more stable than its +2 state, and vice versa for nickel. So if you see over here, nickel, palladium, platinum. So in this group number 10, what we notice over here is the higher oxidation state is shown by element lower down the group. Can you give me example of a compound where nickel can even show an oxidation state of 0? This is a topic which we have already covered. So let me see if you can recall compounds where nickel is showing an oxidation state of 0. Let's see. The next property that we are taking up is electrode potential, and I have the data listed in front of you. Now if you notice over here, electrode potential starting from scandium. Now because we are talking about the reduction potential M2 positive M, that means of a divalent ion and the metal combination. So the metal showing an oxidation state of +2. We are not talking about scandium over here. Can you recall why? Because scandium does not show the +2 oxidation state, right? We have already discussed this. Now go on to the other elements. You notice there is no regular change in the reduction potential for these particular elements. So whereas here it's -1.63, -1.19, for chromium all of a sudden it is -0.91, and then for manganese it shows an increase. It's -1.18, right? Go on further. Something interesting to be seen over here in the case of copper is a positive value of the reduction potential, right? That means it has more tendency to stay in the form of a metal rather than convert itself into an ion. All these values can be explained to more or less extent in terms of the electronic configuration that is listed over here. If you see in the case of zinc, here the tendency to lose S2, the 4s2 electrons will be high, because of which it provides the necessary energy in order to cause the removal. And where does that necessary energy come from? From the hydration enthalpy. Now let's understand that concept as well. When you talk about electrode potential, in the formation of the solvated ion, what are the steps that take place? The metal gets converted into the atomic state. Now this in some places is denoted as the enthalpy of atomization, right? The standard enthalpy of atomization, or in some places you will also find it written as enthalpy of sublimation, right? So you can write it as per your curriculum, whatever is mentioned, right? So enthalpy of atomization. Then that atom gets converted into an ion. Now here I have written a generic Mn positive. What happens over here is metal first gets converted into positive ion. So the ionization enthalpy 1. That's the first ionization enthalpy. Then M positive gets converted into M2 positive, constituting the second ionization enthalpy, that is IE2, and so on and so forth. So generically I have written it as delta HI neta, indicating that the standard value. Now lastly the ion gets hydrated, and the energy that is released over here, understand the difference? Enthalpy of atomization is the energy that you have to give in order to convert it into an atom, or to convert an atom into the gaseous state. Enthalpy of ionization is the amount of energy again that you have to give in order to convert an atom into an ion, because you have to pull the electrons away from it. On the other hand, enthalpy of hydration is the amount of energy released. Why? Because the ion is getting hydrated because of the force of attraction between the ion and the solvent molecules, right? Now, if this energy is sufficient enough to cover the enthalpy of sublimation and the enthalpy of ionization, then what will happen is this reaction, the total energy change will be good enough to carry the reaction in the forward direction, which we notice is lacking in the case of copper, right? That is why it is giving us a positive value. Now, wherever you will find that by loss of 2 electrons, it is acquiring a stable configuration, you will notice that there is an increase in the E0 M2 positive M value. For example, in the case of manganese, the configuration is S2D5. So it has a tendency to get away with this S2 configuration. So it has a D5 configuration. So electrode potential is high enough, right? Same way in the case of zinc, gets rid of S2, acquires a fully filled D10 configuration. So it has a tendency to lose those 2 electrons, negative 0.76 value. All these values negative indicate something very, very interesting. Can you tell me what? Yes, that all of these metals except copper are capable of liberating hydrogen from its compounds, because the electrode potential of hydrogen is 0 volts, right? So indicating that if the reduction potential is lower than that, they will liberate hydrogen from its compounds. That is why we notice that zinc will combine with dilute acids. So zinc reacts with dilute acids to liberate hydrogen from them. We are concentrating, or I am stressing on the word dilute, because the same reaction is not shown if you are using concentrated acid. Can you tell me what will be the product if I am using concentrated acid? Because concentrated acid now acts as an oxidizing agent, right? So with the result, it will form zinc sulfate, water and sulfur dioxide. So you notice the difference in the concentration, how it affects the formation of the products, right? Whereas copper, because it has a positive reduction potential with any dilute acid, H2SO4, HNO3, HCl, if I am taking dilute acids, it does not show any reaction. But copper with concentrated H2SO4, yes, the same reaction as we have seen in the case of zinc. So copper sulfate, water and sulfur dioxide, right? Now, when you have a question pertaining to the electrode potential values, my advice to you would be to see the electronic configuration. See the electronic configuration, form M2, M3 positive. You could also be asked a question on, let's say, we say the reduction potential M3 positive, M2 positive. Now here again there is no regular trend. You cannot really say what is the trend. There's no regular increase or decrease. As I always say in this particular chapter, please see the electronic configuration and you have the answer right in front of you. Always remember, whether you are talking about the metal, the ion, what, divalent ion, trivalent ion, or a single charge. So accordingly write the electronic configuration and the answer will be right in front of you. right? So we've covered approximately 9 properties till now. Would you like to go on? So let's talk about magnetic properties. So whether they are attracted in a magnetic field or repelled in a magnetic field or get strongly magnetized in a you're talking about magnetic properties. So ferromagnetic means they will get strongly magnetized in a magnetic field, external magnetic field. Paramagnetic means they will get attracted in a magnetic field, and the reason for this is the presence of unpaired electrons. So more the number of unpaired electrons in any atom, stronger will be the paramagnetic character. How do we measure it? We measure it in terms of the spin angular momentum, what is called as the magnetic moment in this particular formula. Mu is equals to under root of n into n plus 2. What does this n stand for? The number of unpaired electrons. Mu is the magnetic moment. Its unit is Bohr magneton, Bm. As you can clearly see, mu and n are directly related to one another. So more the number of unpaired electrons, more will be the magnetic moment and greater will be the paramagnetic character. So can you predict around which group will you get the highest paramagnetic character? Remember the concept of unpaired electrons. Tell me which group will have maximum number of unpaired electrons. Is it towards the two extremes, closer to group number 3 or closer to group number 12, or will it be in the middle? Yes, it will be in the middle of your D block, because that is where the number of unpaired electrons is maximum. Great going. So let's finish it off, because there are 2-3 more properties to be done and we should be better placed in terms of the D block elements. These elements, the transition elements, show very good catalytic properties, right? You know about Haber's process, contact process, manufacturing and hydrogenation, where you use nickel as a catalyst, right? So all these examples, you know that catalysts are highly useful, and these catalysts are coming from the transition metal series. Now, knowing their properties, what do you think is the reason that transition elements are able to show good catalytic properties? Yes, the first and foremost is the variable oxidation state. So what they can do is they can change their oxidation state to suit the need of the reactant. So let's suppose there's a reactant and we use vanadium pentoxide, right, in the contact process. So what can happen is that the oxidation state of vanadium here can change in the presence of sulfur dioxide to form V2O4. And this V2O4 again on coming in contact with oxygen can change back to V2O5. So what this catalyst is doing is it is providing a temporary pathway for the conversion of sulfur dioxide to sulfur trioxide. Now what is happening over here is it is getting converted to V2O4, but in the process it is helping sulfur dioxide to convert to sulfur trioxide, right? So it remains unchanged at the end of the reaction. So, and this is only possible because of the variable oxidation states. The other reason is that they are able to form complexes with the reactant. So the reactant binds to the transition metal. So reactant forms a complex on combining with the transition element, right? But this complex, remember, is a temporary arrangement, and what will happen is this complex is again capable of releasing the reactant in the form of a compound into the reaction mixture. So what is happening is this transition metal is only providing a temporary platform for the reactant molecules to come and be friends with each other, right? So it is only acting as a mediator, right? Let's go on to some other properties of the transition elements. Alloys. What are alloys? They are mixtures. First of all, they are not compounds. Mixtures of what? Two or more metals, right? You know about steel, you know about brass, you know about bronze. So we have a combination of two or more metals, or it can be the alloy of a metal with a non-metal, right? Because there are examples where carbon is added in order to make alloys. Now these alloys, they are homogeneous mixtures, right? So the property is the same throughout. Correct? Why do transition elements form alloys? Go back to their atomic radii and you will have the answer to this question. You will not have to memorize it like a parrot, right? Then there is something which is called as interstitial compound. Have you heard about it? What are interstitial compounds? Yes. Compounds wherein small elements, they get trapped within the molecule. So what we've got is, we've got small elements, small atoms like hydrogen, carbon, nitrogen. They will get trapped in the crystal lattices, and these compounds are called as interstitial compounds. So their properties, what do? They enhance the properties of the metal. How do they do that? See, basically what is happening is they are simply getting trapped. There is no proper bonding which is taking place, and probably they are just filling in the gaps in this crystal lattice. So because of which the nature or the behavior of the transition element changes. So although they do retain their tendency to conduct heat and electricity, they remain mostly chemically inert. Their melting point is usually higher than that of the pure metals. You know very well from your knowledge of practical chemistry that the transition elements, they show colors, right? You have the iron compounds which you can identify by their colors. You have the copper which is blue or greenish in color. Same way, other elements, other metals also in the D block show specific colors. Why do you think they show all these colors? Go back to coordination compounds and you will have the answer, right? Just a hint over here. Why do they show the formation of colored ions? Yes, because the electrons in them, they get excited. If you remember, we had spoken about the T2G and the EG levels and the electrons jumping into the higher energy orbitals, and because of the absorption of this energy, the portions of the light which are not absorbed are reflected or they pass through, and that is the color of the metal ion which is observed, right? Here I am not explaining in detail. I want you to go through coordination compounds and be able to answer this question. Talking about coordination compounds, do you remember that we had spoken about a lot of transition elements forming complex ions? Can you recall why they form complex ions? I am leaving it to you to revise, right? I hope you were able to relate to this chapter. We are not yet done. We will be continuing with this in the next lesson, where we will be talking about lanthanide contraction as well as some of the compounds of the D block elements. So stay tuned. Don't forget to like, subscribe and share. See you in the next lesson.